sharing. But you can see there are, like, in terms of the physics, there are very small number of really fundamental ideas here, right? You see the Larmor formula, for example, has appeared in so many cases. Okay, so this I had pre-written. I'm not able to access this material on this Teams platform, but it is there. So, so this is just a summary. Since last time I couldn't do things properly, I've just written this down again. You can see what I'm showing, right? This OneNote thing. Hello.
Yes, sir, we can see it.
Okay, so here are like some of the important things to reorient you again, because last time I was not happy with the way I could scribble on the other software. So this part is angular distribution of synchrotron energy per unit frequency. So this was the diagram that we had, right? That you have like a particle. This is the trajectory of the particle. And this is the plane of this particle's motion. So it's sort of, if you look at in the lab frame, like if you have magnetic fields in the vertical direction, you are in the plane which is in the velocity. Velocity, the plane containing the instantaneous velocity and r of the particle. So this is like the geometry. So if n hat is the line of sight from where you're looking, so you can actually, so if this is the trajectory, you can look from anywhere, right? But we know that only close to the line of sight velocity will you receive a lot of radiation, right? This is because of relativistic beaming, in case where particles are moving close to the speed of light. So that's why whatever direction you choose, you will always see only the particles which are along the line of sight, predominantly those particles which are along the line of sight, right? And these are particles, when I say along the line of sight, they were along the line of sight at retarded time. Right now, they may have moved a little bit away from line of sight. So this was the geometry, and we considered these two polarizations, two basically directions in which the electric field oscillates, this perpendicular epsilon perp hat and parallel epsilon parallel hat. Epsilon perp hat is in the direction of the particle acceleration, acceleration of the particle, and this epsilon parallel hat is perpendicular to n hat and epsilon perp hat, right? This is just the triad. So you had n hat, epsilon perp hat, and this third direction which is perpendicular to both n hat and epsilon perp hat. So this is the power dw perp by d omega is the energy coming at a solid angle omega in frequency omega 2 omega plus d omega. So this is how the perpendicular polarization goes, like as a function of theta and as a function of frequency. And there are these special functions which appear. These are Bessel functions. You don't have to like memorize all these things, but pay attention to things like that this energy is maximum when theta is 0, right? So basically this polarization, which corresponds to the polarization along the direction of the acceleration of the particle, is maximum when the particle is pointing right at you, right? When theta is equal to 0, when the particle is along the line of sight. So you can actually see, and here like gamma theta square is this, and you can actually see that the theta dependence, this gamma theta function goes to right. So this eta eta dependence is here. Right. So this dw perp d omega goes to 0 away from theta equal to 0 at an angle, after an angle corresponding to 1 by gamma. Similarly, this one, the other polarization which corresponds to epsilon parallel hat, vanishes at theta equal to 0. You see there is a theta square here, but it also sort of decays about at the same angle as 1 by gamma. Okay, so this is fine. Right, so this formula does not apply for all thetas. You can actually see that, because if this applied for all thetas, then there is no theta in eta, so this is independent of theta, and there is 1 plus gamma squared theta squared. In fact, this would increase with theta. So I think here this only applies close to theta less than equal to 1 by gamma. Okay, so this only, let me try to draw here. This applies for theta. Okay, so this was angular distribution, the first part, in these two polarizations, perp and parallel. Then this is, if we integrate over all angles, how does the power, which is energy emitted per unit time per unit frequency, how does the power go? So it's just like integral of dw d omega over all solid angles, and then you have to divide it by a time period which is equal to 2 pi by omega b, right? So then we get this. These functions are very commonly used, capital F and capital G, when you deal with synchrotron. And in all books like Ribicki and Lightman and other books, you will find expressions of these. These are like integrals of these Bessel functions K's. Okay. Right. So the other thing to note is that here the frequency dependence is through this X, and X is just this, right? X is just omega by omega c, where omega c is this 3/2 gamma cube omega b sine alpha. So you know, you don't have to memorize any of this, but what you have to sort of have a sense of is that the power, the synchrotron power, right, as a function of omega, only depends on, it's a function of omega by omega c. It does not depend on omega independently. It sort of depends only through this combination. So basically, the other thing to sort of note is that the frequency at which your radiation peaks is sort of roughly equal to gamma squared EB by MC, right, which is equal to gamma cube EB by gamma MC, which is just, I mean, I'm actually ignoring factors of sine alpha when I write these scaling things, but you can actually see this is just omega b. Okay, so if you have cyclotron motion at some frequency, the frequency of the observed photons is much higher by this factor. Okay, so let's sort of do, yeah, so this is important to note. So for example, let's just consider some typical value. Let's say magnetic field in the ISM is say 1 microgauss. Okay, so what will be omega b? Omega b equals EB by gamma MC, right? So let's see. This would be 5 times 10 to the minus 10. This is E in ESUs. B is 1 microgauss, 10 to the minus 6 gauss. Oh my god, this is bad, not good. Divided by gamma. Proton mass is 10 to the minus, sorry, electron mass is 10 to the minus 27 in CGS units. C is 3 times 10 to the 10. So this is the frequency in hertz or cycles per second. So let's see what this is. So minus 20, minus 26. So this so minus 26, minus 27. This gives you 10. So this is about 50 by 3. Let's say 15 3s are 45. 15 by gamma cycles per second. Right, so this is very, very low frequency. I hope I've done this calculation right, because this sounds a little low. E, B, gamma, M, C, minus 16 minus 10. Okay, whatever. Right, so if you have 15 hertz, or
So this is for proton.
This is not for proton, this is for electron. Electron mass is 10 to the minus 27 grams. Proton mass is 10 to the minus 24 grams. This is for electron. You never consider radiative processes, almost never consider for protons, because electrons are much more radiative. Okay, so this is okay, whatever it is. Now let's a lot of times we see radiation is at 1.4 gigahertz. If you look at the Milky Way radiation, synchrotron radiation, you have a lot of it at 1.4 gigahertz. Now if it is right, so this is the observed frequency, this is nu, this is omega, so nu is equal to omega by 2 pi. So 2 3s are 6, 6 3s are 18. Let's say 3 by gamma per second, or hertz. So this is like the observed frequency. I told you that this is equal to gamma squared omega b, which is nothing but or nu b, which is nothing but 3 by gamma, or gamma cube, sorry, now I'm using omega b. So gamma squared times 3 is equal to the observed frequency, which is 1. So let's take it 10 to the 9. So 1.4 gigahertz or 1 gigahertz, I'm just taking 10 to the 9 hertz. And let's ignore just this 3. So you see gamma is like 10 to the 9 by 2. So the particles which are producing this synchrotron radiation have a gamma, this relativistic gamma, which is like 3 times 10 to the 4, right? They are almost moving at the speed of light. These electrons which are producing this 1.4 gigahertz synchrotron. You see this way of estimating the gamma of electrons. So this is where these scalings come in very handy. Okay. Do you get what I was trying to do? So I used a micro Gauss magnetic field, and I said that I am observing synchrotron emission at 1.4 gigahertz. So what is the particle gamma around which are responsible for this synchrotron emission? And I found gamma of order 30,000. Is this clear? Yes, no, maybe.
Yes, sir.
So this type of order of magnitude estimates are very, very useful, because once you get an extremely detailed formula, it will take you for a while to understand what's happening. But these things are very robust, and they'll give you the right ballpark number, right? Okay, good. Right, so we talked about this one, we talked about this one. So this is where order of magnitude stuff comes, right? And we know that the other formula, which is very, very important, is this total synchrotron power, right? Which was like gamma squared UB sigma T C times, there was this 2/3, whatever, you can ignore this 2/3, right? So there is gamma squared energy density of photons, Thomson scattering cross section, right? So this will be an erg per second. So these scalings are very important. Someone asked, like, how carefully should we do the derivations? If you're using this in your research, you have to do the derivations, because this is like the fundamentals on which your research is based on. If you're not doing research on, synchrotron emission, then you can just take these results. But everyone should know these scalings. Okay, this is the way I look at it. I don't know all these formulae, but I do know these scalings very well, for example. Okay, so now this is the other thing that I wanted to show. So this is showing a particle cyclotron orbit, right? And magnetic fields are in the vertical direction, and the pitch angle is alpha, right? So if someone is looking from here, right, and nowhere in the position of this orbit, the velocity is along the line of sight, right? The line of sight is this and the velocity is that. So here you won't see a lot of radiation. But if you are in this line, which is at an angle alpha, which is along at some point of this trajectory, the electron is along the line of sight, and you see this beaming effect. You see this beamed radiation along the line of sight. That's when you see this power, right? That's when these formulae are valid, because I've assumed theta less than equal to 1 by gamma. So in this particular example, most of the radiation will actually come in this solid angle along this direction, which is alpha pitch angle direction. I mean, distributed about a small angle of order 1 by gamma. That's the content of these quantitative formulae, that the radiation is mainly along this direction. Now, suppose you're looking at this from this direction, you don't have a single distribution, you don't have a particle population which just has single alpha, right? Some particles will just go like vertically, zipping along vertically. Some particles will go horizontally, almost horizontally with alpha equal to 0. Some, there is a distribution of alpha. Oh my God, this is really bad. All right. So so it depends on where you are looking at. You will choose a particular alpha when you're looking at some particular n hat. Right? Only those pitch angles which are aligned along your line of sight are the particles that you will see, really. Okay? Is this clear? This one? Yes?
Yes.
Good. Please speak, otherwise I feel like I'm speaking to the walls. Okay, so wow, it came here. Okay, so this is really recap from the last time. What's most important is to know exactly what we are doing. No need to know the formula in detail or anything. Scalings are useful. So I'll actually close it and I'll go back to what I like using, which is this. Okay. Okay, so now let's start with today's class, really. Okay. Okay. Okay, so just last thing. Right. So let's actually. No, so suppose you're looking particularly along that line of sight. What will you see? Right, this particular line of sight, which corresponds to the exact angle alpha, means that theta, which is relative to this velocity direction, is 0. So you won't see this because theta equal to 0. This radiation is 0. Energy in this radiation is 0. There is proportionality to theta square. This is maximum for theta equal to 0. So you will only see this polarization along this direction. But if you're slightly off from this direction, right, you will see, so here you will see linear polarization, right, because you only see this particular oscillation of electric field. You don't see this. But if you're slightly off, you will also see a component of this. So in general, you will see elliptical polarization. In general, elliptical polarization along a line of sight if for a fixed alpha, for a fixed pitch angle. But in almost all situations, your alpha will not be fixed. You'll have particles which have a distribution in alpha. So what will happen is the particles which have slightly higher alpha will be sort of emitting in this direction. Particles which have slightly lower, smaller value of alpha will be emitting in this direction. So this the elliptical polarization of one sense will get cancelled by elliptical polarization of another sense from the particle which has a slightly different alpha. Okay, so what you get is a high degree of linear polarization. Okay, and that's because of dominance of this guy. This dominates over this one. The perpendicular polarization, which is along the direction of acceleration, dominates over the other polarization. So let's actually talk about polarization a little bit. So okay, so let me draw. Suppose this is the magnetic field on the sky. Oops, that. So suppose this is the direction of magnetic field on the sky. Right, so it's large scale magnetic field, and and particles are gyrating around these. And suppose this is the direction from which you are watching, and this is your n hat, right? So your polarization is always perpendicular to n hat. So what you do is you draw this plane perpendicular to n hat. So you will have one polarization which is along the direction of the, so this is polarization along direction of projected magnetic field. Okay, so this is parallel polarization. This is along the direction of projected magnetic field. And then you have this other polarization, which is the perpendicular polarization corresponding to this guy, the epsilon perp hat. This is the P perp and this is P parallel. Okay. So, and this is relative to the direction of projected magnetic field. So projected magnetic field means that, how does the magnetic field orientation look like on the sky? Okay, I did not turn on my video today. I can actually turn it on. Okay. Right, so this is perpendicular, this is parallel. You can actually see because the acceleration direction is perpendicular to the direction of the magnetic field, right? The direction of acceleration is always perpendicular to the direction of the magnetic field. That corresponds to this polarization or this one. This is this other one, the other polarization. So what is the degree of polarization? Pi, degree of polarization. And again, we are actually assuming that these two polarizations are adding incoherently. And that's a good assumption because you're considering a distribution in alphas and so on, right? You're considering population of particles which have some spread in their pitch angles, and the magnetic field is not perfect. So the coherence is not there among the particles which are emitting, right? So you have to treat this and this as incoherent linear polarization, right? So you cannot add them, for example, vectorially and get, if you add two linear polarizations, you get linear polarization. Here, they have a random phase between these two. So it has polarization, a polarized part and an unpolarized part because of this random phase that we consider. Right. And even though if you have a distribution in alphas, when you're seeing at a particular direction, you're picking out a particular alpha, right? You're picking out a particular pitch angle because only those particles are beamed towards you. Okay. Do you get this point, right? Whichever direction you're looking at, you will pick out the particles which are at some point of their trajectory beaming directly towards you. So this is pi. This is what? This is I max divided I min, p perp minus p parallel divided by p perp plus p parallel plus p parallel. This is the minimum. This is the minimum intensity divided by maximum intensity, and this is degree of polarization. Right. So right. So this is polarized intensity. This is polarized intensity in the numerator, and this is total intensity when you add them incoherently, and this is when you are when you cancel and these are the two principal axes, right? This principal direct axes of polarization ellipse. You remember from your Stokes I, Q, U, V. These were the two directions these are like your x prime, and y prime, if you will recall the notation that we use there. So this is equal to, if you look at these formulae, right? So these, p perp minus p parallel is just g by this plus this is just f, right? This is this function of omega by omega c. So this is degree of polarization, and g is of course always less than f. So this is always less than 1. But the degree of polarization can be as high as 75% for synchrotron emission. It depends on, so basically 75% correspond to the maximum of f by g, right? For a particular omega by omega c. Is this clear? This discussion of polarization, because this is actually quite important. Because why is this important? Let me open what I wanted to show. Right, for example, here are some of the observations of like a face-on galaxy, and you see here these lines in this. Can you see it? There is like contours, which are the contours of radio intensity, but there are also these lines, like these dashed lines. Here they are very, very clear, right? Here are these dashed lines. Here also there are these dashed lines. Can you see them? Hello?
Yes, sir.
So these dashed lines are, so we know that the perpendicular polarization dominates. So the direction of polarization is sort of perpendicular to the projected magnetic field on the sky. So if you just draw perpendicular, locally perpendicular to the direction of polarization, that would be the local magnetic field direction, projected local magnetic field direction. So you see here, and the length of this this is perhaps proportional to the degree of polarization, right? So the longer this dash is,
Sir, what are the contours? What do the contours signify?
contours signify the radio flux, how much
Okay.
radio power comes per unit frequency. So this is very intense at the center and intensity decreases. This is like a jet, not an M87 jet, right? So these are intensity contours, and intensity is generally higher towards the center of these things. Now these just dashes correspond to the length of these dashes correspond to the degree of polarization, and the orientation of these dashes is perpendicular to the polarization direction. So this direction corresponds to the magnetic field direction of the projected magnetic field. So you can actually see in these spiral galaxies, if you could actually see these dashed can you see these? Can you see these lines? Dash, 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 dash. Can you see these?
Yes, sir.
Yes, sir.
Okay, so the idea is that this is the direction of local magnetic field, the projected direction of magnetic field. So you can actually see that these spiral galaxies, magnetic fields are almost arranged along the direction of the spiral. It only tells you about the projected magnetic field component. So the projected magnetic field component in this image is mainly in the phi hat direction, and that also is expected from theory, right? And here the projected direction is sort of along these walls, right? Here you don't see a lot of polarization. That means magnetic field is very tangled, right? Because if you have tangled magnetic fields, all these polarizations do not add up coherently. But if you have regular magnetic fields, there your degree of polarization will be high. So polarization is actually very, very important to infer such things. Do you get the idea? You see here in this one, the author has also marked these arrows. So the magnetic field is in this direction. You can actually see this hint of it sort of undergoing these large scale oscillations, right? Then it sort of points in that direction, again points in this direction, points in that direction. It's almost like a wavy feature in the direction of projected magnetic field. Oops. You saw that, right? This. Oops.
Yes.
Right. Okay, so this is actually the importance of polarized radio emission. It can actually tell you something about the geometry of magnetic fields perpendicular to the line of sight. And it only is sensitive to line of sight because if you have magnetic field which is pointing towards you, right, your acceleration is if you have a magnetic field which is pointing towards you, the particles gyrate perpendicular to that direction, and you don't see this epsilon perp hat component because the particle velocity towards you, the circular motion is not seen by this line of sight basically. Okay, what else do I have? Okay, so this is important. I will share this with you too. Okay, let's see. So this is about polarization, very important topic for practical determinations of magnetic field geometries and so on. Okay. So we already talked about that. As you increase the frequency, as you increase the relativistic, the gamma of particles, if particles are non-relativistic, you see circularly polarized light and linearly polarized light, depending on where you are looking at. But if your particles become relativistic, you start seeing higher and higher harmonics. And again, if you have like a distribution of alphas and a distribution of magnetic fields, then you get almost a continuum radiation. So actually, let me go back to this guy. Right. So this F and G functions, let me just tell you right here. This is actually important. I did not point this out. F goes like x to the 1/3 for small x and cuts off exponentially at large x. So what does it mean? It means that the so let me actually just draw. So this is power due to a single electron, as a function of frequency, right? Right, fx goes like x to the 1/3. So this function will go like, right, total power is p perp plus p parallel, that's just f, right? Because the frequency dependence is all in x here. So that's, so single electron, synchrotron power goes like omega to the 1/3. So this is a log plot. So that's why omega to the 1/3 is linear on this. And then at higher frequencies, there's an exponential cutoff. And this corresponds to omega c, right? When omega is of order omega c, there is an exponential cutoff. So this is a single particle spectrum. Now, if you recall, we had considered this power law distribution of particles. You recall that we had considered like not a single particle, but if you have n gamma d gamma is proportional to gamma to the minus p d gamma, sorry. Right? Do you remember this? We considered a distribution of particles in energy or in gamma. What happens in that case is, what is the total power due to all these electrons as a function of frequency? So you will have these guys for individual, sorry, this is power law. So this is nu to the 1/3, omega to the 1/3, omega to the 1/3, and then there are these exponentials, right? And all these add up, right? You have to, basically what you have to do is p omega n gamma. This is what we did, like mathematically, this is what we did to get p total due to all these electrons as a function of omega, right? You recall this? We did this, minus p, and then we got nu to the minus p minus 1/2 and b to the power of 1 plus p/2, something like this. Am I right? Let me just, do you remember this? Someone please speak up. Forgotten. Yes, this was that formula. So we got in the end, after doing this integration from gamma min to gamma max, we got this proportionality, right? So basically, diagrammatically, what we are doing is exactly this, that we are sort of adding up all these single particle contributions, weigh them according to this guy, right, and add them up. So you get something like, sorry, the envelope of these, and this is omega to the minus p minus 1/2. You see what I have done? Can someone please speak up? I am adding these single particle contributions to get the power, total power, as a function of frequency. Does this ring a bell? We have done something like this earlier. Multicolor black body, multicolor disk. Homework set 1. And in fact, it appeared in exam 2. Multicolor disk. Does anyone see the connection? Yes, no?
It's 1/3. 1/3 was there.
Right.
Total
So, no. Connection is not that. What we are doing is we are actually doing almost the same thing, right? There we had these B news, right? All these rings contributed to their black, their local black bodies, right? So you had, in this case, in the multicolor black body, all of them actually had this new square at low frequency and then the exponential cutoff, and their weightage was according to the area that these rings had, right? And then we just added them all up and it gave rise to nu to the 1/3, right? You remember this? F nu or I nu or power nu as a function of nu. All you did was this, add up all these black bodies and got something which was very shallow, nu to the 1/3. Here also you're adding up these single electron power distributions, but you're weighing them with this factor which corresponds to their distribution in energies, right? The procedure is almost identical. The idea is that you know how a single particle or a single ring here, a single ring here emits, and then you add them up, all the rings, using the weighing, appropriate weighing. Weighing is the idea. Here you're weighing by areas, here you're weighing by n gammas. Do you get it now? The connection that I'm trying to say, that this is just a coincidence that this is 1/3 and this is 1/3. The idea that you can combine these universal single particle or black body type things, combine them appropriately according to a physical situation and get a result which is somewhat different, which appears different. Okay? That's the idea, right? Someone may ask, a single particle gives you omega to the 1/3 and exponential cutoff. How come this distribution of particles gives you a power law, which depends on P? It's because of this weighing. In the same way, single black body gives you nu square and exponential cutoff. It's the combination which is weighted by the area that gives you nu to the 1/3 in some range. Got it? Yes. So, these concepts are very important. This type of concepts are very, very important. These numbers and formulae are not. Okay, let's go to what we want to do now.
Your time will come, Diana.
Oops.
You'll become all that you dream of and more.
What was that? Are we being attacked by aliens? Okay. So now we'll do synchrotron self-absorption. Synchrotron self-absorption. Right? Absorption and emission are fundamentally related processes. We know that by Kirchhoff's law. So can we sort of calculate the properties of synchrotron absorption? So what happens in synchrotron? So in synchrotron emission, you have these particles which are gyrating around magnetic field lines, and they emit photons, right? In synchrotron absorption, you have these particles gyrating around. You have some background light. This light can give energy. Photons can energize electrons and lose energy. So in this case, there is transfer of energy from particle energy to radiation. Here, there is a transfer of energy from background radiation to particles. Okay, so this is emission. This is absorption. I mean, so in fact, here you can actually think of, like in the photon picture, right? You have a, there is no photon at the beginning, but because of this accelerating charge, you have photon emitted. Here, there is photon and there are some particles. This photon will give its energy to, motion and get absorbed. So just like, when we talked about line emission, line absorption, you can have this continuum emission and absorption. Continuum in the sense that there are no discrete levels, right? Whatever the energy of the particle is, you will have some gyro orbit, right? So there, you are at, your energies are so high, your particle energy is so high that the Larmor radius is much bigger than, say, your Compton wavelength. This is equal to h by MEC. This is the Compton wavelength. This is sort of like if you have electron moving at close to speed of light, this is the de Broglie wavelength, right? So electron de Broglie wavelength. When is quantum mechanics important? When the size of the orbits become of order the de Broglie wavelength. So if your orbits are much bigger than the de Broglie wavelength, you can ignore quantum behavior or discrete energy levels, which are called Landau levels in this case. Now that only happens for very high magnetic fields. So we are just ignoring this part. We are just doing continuum. Okay. So now let's sort of, let's consider two energy levels, 1 and 2. Okay, and so we are considering absorption coefficient, alpha nu. If you recall our chapter 1 from Rybicki and Lightman, we could write alpha nu in terms of Einstein's coefficients. So, Einstein's A21, B21, and B12. If you recall these Einstein coefficients, these are those. So alpha nu, the absorption coefficient, we could actually write as h nu by 4 pi and summation over E1, summation over E2. E1 and E2 are these energy levels, and these energy levels differ by h nu. So since you have continuum of levels, you can consider all the levels which differ by h nu. So you can actually consider these or something else. So there is a continuum of E1 that you have to add up and continuum of E2 that you have add up, such that they also differ by the same h nu. Okay, so N E1 B12 N E2 B21. I mean, this formula we had actually written when we were doing chapter 1, pi to 1 times, right? What is this? This is the macroscopic absorption coefficient. These are Einstein's B's, right? If you recall, this is stimulated emission, right? Stimulated emission corresponds to negative alpha nu, right? This is line profile, right? How sharp is the is the difference between these two energy levels. And it's sort of like a delta function if the transition is sharp. So this has a unit of 1 by frequency. Okay. This is number density. So this is number per unit volume of particles in level 1. Similarly, this is the corresponding thing for level 2. B12 is proportional to the probability of transition from level 1 to 2 in presence of photons. This is of course the energy of the photon. This is divided by the total solid angle. So we are assume isotropic B fields. So the magnetic field is not regular. It's sort of tangled. Right? Magnetic fields are tangled so that you can treat all directions as equivalent, isotropic magnetic field and isotropic alpha. So these can actually be generalized, but for this case we'll only do isotropic. Otherwise it becomes quite complicated. Okay, is this clear? So the more you have in energy level E1, the more you'll have absorption. Similarly, if you have more atoms or or more electrons in this state too, then you'll have more emission, stimulated emission. So this is alpha nu. So we have assumed this, and for this case we can actually call the power. Let me just write power nu E2 is equal to 2 pi power omega. So this is, I'm just calling this is the power emitted, or this is really synchrotron power, because that's what we are considering. Synchrotron power emitted for particles with energy E2 that emit photons of energy h nu, of course. Okay, and this is just 2 pi that comes from going from nu to omega. Okay, so we know this P nu E2. What is P nu E2? This is nothing but, this is h nu summation or E1 A21 phi 21 nu. Right, this is just spontaneous emission formula. Right, so if you have Einstein spontaneous coefficient A21, then this is the energy of the photons. This is probability per time for downward transition, and this is of course the line profile. So this is probability per unit time, energy per unit time, per unit frequency. This is this is nothing but energy per unit time, per unit frequency. Okay, and we know that A and B, Einstein A and B coefficients are related. So Einstein A 21 is equal to twice h nu cube by c squared B21. And these are fundamental. This is true, always true. Although these are motivated from the appearance of the black body function, these relations are always true for all microscopic processes. Okay. So this is, so this guy then becomes equal to twice h nu cubed by c squared times h nu summation over all E1, right? You know, once you fix E2 and you allow nu to vary, then you have to sum over all E1. But this delta function will also sort of fix E1, you know, because it only contributes when E2 minus E1 is equal to h nu. So summation over E1, so B21 phi 21 nu. Okay, so this is the emission. Okay, so now what we'll actually, so the plan is actually to write this, you know, the fundamental thing that we have done till now so many times is relate. So first we calculate emission properties, then we invoke Kirchhoff's law type ideas, and then express absorption in terms of emission itself. Okay, so that again we are sort of doing the same thing, except here the synchrotron emission mechanism is not a thermal mechanism. So your S nu is not equal to B nu in general, because this is, you can have a non-thermal particles. So that's why we are doing a more general treatment. Okay, so this is fine. So this is P nu E2. This is about emission, power emitted. Okay, so let's look at the stimulated emission part of alpha nu. Let's look at that. So let me actually, you know, we may need this, so let me highlight this. I mean, Kirchhoff's law is so fundamental. This is absorption related and this is emission related. Okay. So let's write this down. So this is what stimulated part of alpha nu, which is this guy, right? This is the stimulated part of alpha nu. So this is h nu by 4 pi summation E1 E2 n, okay, so minus sign, n E2 B21 phi 21 nu. Okay, so but from here, from this relation, we can actually write this summation E1 B21 phi 21 nu in terms of the emission. So this is equal to minus c squared by 8 pi h nu cube summation E2 n E2 power nu E2, right? You see, the thing was to be able to write these microscopic coefficients in terms of the emitted power, for which we know the formula. So what I have done is I've just replaced this summation. I just replaced this by the above expression. So summation E1 phi 21 B21. I'm just sort of using this above expression, and this h nu cancels. This 2, this becomes 4. So this is what you get, right? You see what I'm doing. Okay, right. So, and you know, the same thing can be done, right? So B12, we also know that G1 B12 is equal to G2 B21, right? This is another of proper relations between, so that, you know, you have this guy, you have this guy. This is fundamental. This is always true. Again, this is always true, where G1 and G2 are the degeneracies of level 1 and 2. And for these particle orbits which have almost comparable energies, G1 and G2 are equal. So B12 equals B21. So we are considering particles. So h nu is equal to E2 minus E1, right? These particles are relativistic electrons, so they are sort of going in at least MeVs, if not more, right? H nu, we're observing synchrotron, radio emission, right? Radio emission is very, very low energy compared to MeV energy, right? So basically E2 is almost equal to E1. They differ by small amount, okay? So the degeneracy factor is almost the same for these continuum particles. Okay, so yeah, this is the stimulated part. We can now combine now the full. This is alpha nu is equal to c squared by 8 pi h nu cube summation E2. So now I'm actually also substituting for this guy and using this relation B12 equals B21. G1 is equal to G2 here. So summation over E2 n E1. So E1 is nothing but n E2 minus h nu, right? E1 is just E2 minus h nu. Minus n E2. And that delta function in phi nu, of course, is gone now. E2 P nu E2. So this is your alpha nu in terms of your emission properties and in terms of your number of particles at two different energy levels which differ by h nu. Is this clear? This is an important formula too. Kirchhoff's law all over actually. We did this for Bremsstrahlung, we are doing it here. Because we want to relate emission and absorption. Okay, so and notice this is important to note that this is NE1 and E1 is E2 minus E1, so this is just this is the same thing. So this part is what we did above, this part. But this part is done analogously, except that here you have NE1. You have NE1. And we have to say that N evaluated at E2 minus H nu, which is E1. Good. So you have this for alpha nu. Now we have this expression for alpha nu. And we will need like the distribution function of electrons. So for example, Fp D3p, we know this thing, distribution function is equal to number of electrons per unit volume with momentum between P and P plus dP, right? But if we consider isotropic particles and isotropic magnetic fields, this can actually be written as 4 pi P squared Fp dP. Okay, and so number of quantum states, so number of states per unit volume is equal to G, the degeneracy factor, by H cube times D3p, right? So this is the number of states, right, per unit volume for momentum in this range. This is just the first thing that we do in statistical mechanics. This is the degeneracy factor. Okay, now so what we are actually trying to do is we are trying to write this in terms of your F. This is what we want to do. We want to write these N's in terms of these F's. Okay, so let's just do that. C squared by 8 pi H nu cube. And this summation we can actually integrate over, replace it by integral D3P2 F P2 star. This P2 star is nothing but this corresponds to E2 minus H nu minus F P2 This corresponds to energy E2 times P nu comma E2. So this is what we have to do. So this corresponds to E2 minus H nu. This is the energy of level E1. Okay. So this is what we have to do. Let's see. So now we'll actually consider two cases. Let me. Okay, so let's first consider thermal electrons. What is meant by thermal electrons? Thermal electron means that their energy distribution is Maxwell-Boltzmann. So you have Fp is equal to K e to the minus by Kt. These are thermal electrons. So this is their Maxwell-Boltzmann distribution. So in this case, what happens is Fp star minus Fp is equal to this is equal to K e to the minus E2 minus H nu by Kt, and T is the temperature, of course, e to the minus E2 by Kt. This is equal to Fp2. P2, let me just put P2, that's what we have here. Fp2 e to the H nu by Kt minus 1, right? This is what we have. This is the energy, this is the F difference between F. Right. So what do we have? So if we plug in this formula, what do we get? For thermal particle distribution, alpha nu equals c squared by 8 pi H nu cube integral for d3p2 Fp2 e to the H nu by Kt minus 1 times the power formula. Okay, now what is this? So this can come out of the integral because this does not depend on P2. E2 is of course dependent on P2. So what do we have? We have right, so what do we have? Okay, let's see this. So 4 pi J nu, this is emissivity, is equal to integral d3 P2 Fp2 P nu E2, right? This is nothing but this is total power emitted by at a frequency nu, emitted by electrons with all at all levels E2, right? So we can actually replace this integral. So what we have is J nu is equal to J nu by B nu T. Actually, if you look at it, this is nothing but 2H, right? So this 4 pi, part of it is just do, then there's a 2 remaining. So 2H nu cube by C square e to the H nu by Kt. That's nothing but B nu 2, B nu T. So this is alpha nu as it had to be for thermal electrons. You see, this is S nu, right? In general, alpha nu equals J nu by S nu. S nu is equal to B nu, right? So this is for thermal electrons. Do you see this? That this had to be true because this is Kirchhoff's law, and S nu is B nu for thermal distribution of particles. Whether it's relativistic or non-relativistic doesn't matter. Okay. What about relativistic? Just a sec. Right, so we can actually manipulate this and we can write it as, let me actually just write it and then I'll just motivate it. Alpha nu is equal to minus c squared by 8 pi nu squared integral dE p nu comma e. See, nu is the photon frequency, e is the particle or electron energy, e squared dou e of Ne by E squared. So this is what I get. So there is a one-to-one relation between E and P. This is for ultra relativistic particles with E is equal to Pc. So it's just a change of variable. I can write, P is equal to E minus h nu, and I make this assumption that h nu is much less than E, right? So then it's sort of like is a Taylor series expansion, right? This guy, you can just Taylor expand. This is nothing but Fp2 okay, so this is Fp2 star is equal to Fp2 minus h nu by C times I mean, let me not write the exact formula because it's slightly, let me just tell. Come on. Okay. So what do we have to do? We have to do this change of variables using E equals PC. So this, right, so what is this? So this is equal to 4 pi P2 squared dP, and this is so how is Ne and Fp related? So Ne dE, right, is equal to 4 pi P squared Fp dP, right? This is just, there is a one-to-one correspondence between E and P, and we know that we also know this. So F is proportional to N by P squared. So there is N by E squared. So that's why you get so you get so Fp is equal to Ne by 4 pi. P is E by C, E squared, C squared. And then you have dE dP. dE dP is C. Right, so this is what you get. So Fp is proportional to Ne by E squared. Okay, so because of that you have this d ne de, dou by dou E of ne by E squared. Okay, because this is like, df. So this is what you have, and then you had this 4 pi p squared dp is nothing but ne de, or d3p is so this is nothing but fp times d3p. Right, so just a second. Okay, so so this is D3P2, this is okay, let me just do it. So D3P2 right. So FP, so DFP is equal to D by DE NE by E squared DE, or and so, right. So there is this E squared DE just comes from P squared DP. So, let me just write down the final. So there are two ideas here, right? One is this idea, so that you can do a Taylor series expansion, that the energy between the levels E2 and E1 is very small compared to the energies themselves. So you can do a Taylor series expansion and do this. The other idea is, the idea of relating this absorption and emission. So, the final expression, once you do this change of variable from momentum to energy, is this. So alpha nu is equal to minus c squared 8 pi nu squared integral dE p nu E. So E2 has been changed to E. This is just a dummy variable of integration. E squared tau by tau E NE by E squared. This is your final expression in terms of distribution functions in energy. So this is your absorption coefficient. I mean, it looks very, very similar to this one. No, it had to be. It has to, because E is just equal to PC. And
So,
yes.
sir, in previous one, denominator is nu cube, and here it is nu square. I think that both should be same degree. I don't know, but
Let's see.
because nu, you just
a second. Let me see. No. It is nu squared, because when you do this Taylor series expansion, this delta E between the two levels is h nu. Right. So this is really this. Right. So this is really this Taylor series expansion of this. So that will give you h nu, and that cancels this h nu. You see what I'm saying? This is evaluated at E2, this is evaluated at E2 minus h nu. This is a Taylor series, so you will have an h nu in the numerator, which cancels h nu from the denominator. That's why there is this. Get it?
Yes, sir.
Okay. Yeah, that's correct. So this is the final expression. Because in the end you should not have any h in your formula, because if we apply this in the Rayleigh-Jeans limit, you should get something which is independent of h. Okay, let's see. So now we can actually right. Let us see. So this is the formula, and let's actually consider ultra-relativistic thermal particles. Then you have Ne equals k E squared e to the minus E by kt. So actually you have to be, you have to just be a little careful about this factor of p square appearing somewhere and not somewhere else, right? This Fp is not Fp d3p. This Fp, in fact, sorry, this Fp is Fp d3p. That's why it doesn't have that E square formula. This is something which does not, which has p square here. So one has to just be consistent, because you can either use this or you can use this to denote your distribution function. So that's why you have an extra E squared here, whereas here you don't consider that, because this is really Fp in this sense. So you have D3p multiplied to this to get the number per unit volume. Okay. Yeah, again, it's useful to go through these, but more important for general students, it's useful to appreciate what it means. Okay, let's see. If we plug this in, Ne by E squared is just k e to the minus E by kt. So you need DDE of this. This is nothing but minus 1 by kt Ne, right? And then you have E squared dE. So this alpha nu, if we apply this above, is minus C squared 8 pi nu squared integral dE P nu comma E E squared Ne by kt. This is equal to this is nothing but J nu, right? This is nothing but emissivity, right? So this is power due to a single electron with energy E, and this is the total number of electrons. So you integrate it over. So this is equal to, and this divided by 4 pi is J nu. So this is equal to minus C squared by 2 kt. 1 by nu squared times J nu. And this this minus sign will right. So this minus becomes plus. So this is actually plus. Right. So the alpha nu, you remember, is equal to J nu by B nu. Of course, again, this is true. Here we have used this Rayleigh-Jeans limit. We have used the fact that h nu is much less than energy of the particle, right? Or which is kT, right? So we have used the Rayleigh-Jeans approximation when we do this Taylor series expansion. We have assumed that h nu is much less than E. So that's why we match the Rayleigh-Jeans expression. But this is again thermal, again ultra-relativistic thermal. We can actually think about, oops. What about relativistic non-thermal, right? For example, Ne is proportional to e to the minus p dp. Like, we consider dE. We consider this type of distributions previously, where particles are power law. So this is non-thermal power law. So in this case, of course, n by e square is like e to the minus p minus 2. D by dE is just d by dE. So this is equal to minus p plus 2. And then you also have e squared outside. So there is an e squared outside. So this is just minus p plus 2 Ne by E, right? This is nothing but this. So if we look at alpha nu expression, this is equal to, so there's a minus there, there's a minus here, so it will be c squared by 8 pi nu squared integral. So there's p plus 2 which comes out, and this e square and that, yeah. So there is so p e p nu comma e, actually, just a sec. dE, I'm just applying this formula. P nu comma E, and this is just Ne by E. Now we have to actually use this P nu E, right? We know, we have actually calculated this. We have calculated this, right? So P nu E, this is more complicated than this, because here we could just write it as J nu, because this is exactly J nu. The definition of J nu is just this. Here we have more complicated integral, right? This is not just P nu E NEDE. There is like a 1 by E lying around there. So here, in fact, that 1 by E became KT, and it could be taken out of integral. Here we have to calculate this, and what we'll use is this power formula, if you recall, was equal to so in alpha divided by 2 pi mc squared fx. If you recall, there was this x equals omega by omega c. So we have to actually plug all that in, and we have to do this integral. It's somewhat messy. It will be sort of an integral of fx, it will right. So there is this x is omega by omega c. Let me actually just tell you what omega c was. Omega c was proportional to gamma cube omega b, which is proportional to gamma squared b. So I'm ignoring all the dependencies on particle mass and other fundamental things. So this was this, but we know that E is equal to gamma mc squared. So there is we can just replace gamma by E. So omega c is proportional to E squared b. Okay. Now, right. So this alpha nu will be proportional to p plus 2 by nu squared, and so we have to do like a change of variable from E to this x. So so you'll have a lot of messy expressions. In the end, what we get is if we the main actually thing is just the dependences on energy. So let's actually just do it. So let's actually just do it. At least see the dependencies. Okay, so this is right. So this is proportional to E squared B. So E is proportional to omega C by B to the 1/2, and X is equal to omega by omega C. Omega C is nothing but E squared B, right? You just see it from here. Omega C omega C is proportional, so X is proportional to this. So there is a this relationship between X and E, which is given by this. So if we do this change of variables from E to X, we get an integral. And let me not do all this algebra. Let me state just the dependencies. So alpha nu is proportional to nu to the 2.5 and b to the -1/2. If you do all this, you'll have like gamma functions and whatnot, complicated things, because there will be integrals of fx dx. So this is what you get, and sorry, not. So this is s nu, not alpha nu. This is, we'll get s nu. S nu is proportional to this. So what was S nu? S nu was equal to J nu by alpha nu. So if S nu is proportional to this, J nu, so J nu is proportional to nu to the minus P minus 1 by 2 B to the power of 1 plus P by 2, right? We know this, we had done this. If you have a power law distribution of electrons, this is how J nu goes. And this is how alpha nu will come from this messy integrals. And we know that this S nu goes like this, irrespective of P. So your alpha nu will, will just go like, will depend on P. Now, if you recall, S nu goes like, it sort of goes like B nu. And in the Rayleigh-Jeans limit, it is just KT nu squared by C squared, or thermal Rayleigh-Jeans limit, right? Now, in this case, you can actually think of KT, you can replace it by like an average energy of the particle, okay? And we know that the average energy of the particle, or the main energy, or h nu of the particle, is proportional to, so right, so you have to use right, so gamma is B you have to use this, right? So the energy of the particles, or gamma of the particles, is proportional to nu by B to the half. So energy is just nu by B, square root of that is proportional to that. So if we plug that in for S nu, where we just replace KT by the energy of the particles which are responsible for radiation, then we get this dependence, right? It's proportional to nu to the 2.5 B to the minus 0.5. This is actually a nice physical way of doing it. You have the same expression. See, here only the algebra is difficult, because you have to do these change of variables. But in the end, you get, so there is no KT in this, right? There is no KT here. Unlike here, there is a KT which comes down in the denominator here, and the integral is easy. So KT has to be replaced by something which is energy. And we know that the energy of photons that we are receiving, h nu is equal to EB by MC. This is why this is so important, times gamma squared. And gamma is nothing but energy. So E is, therefore, E is proportional to nu by B square root. That's why we replace KT by average energy, and that is nothing but square root of nu by B. So that's why we get this S nu. You get it? I think we'll have one more class, or half more class, on synchrotron radiation. Okay. I'm sorry for exceeding. This material is a little dense. Okay, so we'll have half more class on synchrotron radiation. Please read the book. Okay, otherwise you won't really get a lot of these ideas. Okay, then I will end the class. I'll stop recording. Unless you have final questions, I can wait for that.